thanks to the organizers for the pleasure to be here and for this conference for Philippe, who I met first, I think. Well, he was giving some talks about his work with Paul on these nice acronyms, ASM, TSS, CPP, and so on. And actually, it has some influence on me because then I turned to biblical studies, and namely, I studied triangles called Gog and Magog triangles. Of course, this is Zeilberger terminology. Essentially, these are the same things as the ones that Philippe was studying. Okay, so today I will. This is the. Yes. Okay, so today I will talk mainly about maps, essentially planar maps. So I think that by now everybody knows what is a planar map, and everybody is convinced that this is more or less a triangulation of the plane, so I don't think I have to explain this picture here. Of course, there is a huge literature on the maps, and many of this literature is in relation to other topics, and I will cite only two papers, two by Philippe. So the first one is about matrix integrals and the counting of maps and connection with physics. And the second one is about bijections. Bijections in this case with tree-like structures, and it's also a very well-known paper by Jérémy, Philippe, and Emmanuel. And the point of doing bijections is that, maps are objects which are not so easy to understand, and tree-like structures are much easier to handle, and especially if you want to do enumeration or scaling limits or things like that. So it's good to have bijections. Okay, so what is the purpose of my talk? Is to give a general construction of planar triangulations, more generally of planar maps. You will see some examples in the following. Starting from lattice paths in the plane, and using some construction which is called mating of trees. Okay, so maybe not everybody is familiar with all this, so I will give first not a definition, but I will say what mating of tree comes from. It comes from complex dynamics. In complex dynamics, what you can do is something called mating of polynomials. And what you mate are Julia sets of polynomials, which are some subset of the complex plane. And these Julia sets, sometimes they can be dendrites. Dendrites are just continuous trees. And here is, for example, a picture which is taken from Arnaud Cherita's web page. So Arnaud Cherita works on complex dynamics. And if you look, you see this sphere which is decomposed into two subsets, which is one which is more or less white, and the other more or less, I don't know, pink or red, and which look a bit like trees. So I will not try to explain what this is about. You can go to this page, and actually this is part of a movie, and you can run the movie. It's quite nice. You see these two trees mating. Okay, so this construction has been used by Le Gall and Paulin, and then by Duplantier, Miller, and Sheffield in the context of random maps, in order to produce random maps from continuous paths in the plane. But there is also a discrete model for this construction, and the origin of this model can be, I think it goes back to the work of Mullin around 1967. There have been recent surveys by Green, Holden, and Son, or by Sheffield in recent years about this, about both the discrete model and the continuous limit. And what I will explain is how it works and how to do some little generalization of it, which yields some nice bijections. And since I'm the last speaker of today, and we had quite a lot of talks, so I thought I should do a relaxing talk. So this will be there will be no formulas, only pictures, and I hope easy to understand pictures. So maybe not everybody here does agree with this definition of relaxing. but okay. So the first is how you go from paths, first from paths to trees. So on the left you have a dig path, so which I see as a one-dimensional path because the vertical dimension is the dimension where the path takes place. And well, of course, there is a well-known way to transform that into a rooted planar tree. What you do is, one way to see that is you take out the striped area which is below the path and you just glue the opposite steps. Okay, and you obtain this. And of course, you can go back and just by making a contour exploration of the tree and get back to the dig path. You can also do that to mock skin paths. In mock skin paths, instead of having up and down steps, you have also horizontal steps. Well, when you do that, what you do is you just crush the horizontal step, so you lose a little of information. So it's not a bijection in this case. But nevertheless, we will use this kind of contraction. So I will call this a contraction of path into a tree. Okay. It's also possible to consider paths which do not necessarily start or end at zero. For example, for this path, what you do is each time you have an up step which corresponds to a down step, you do the contraction, but so there remain some steps which are not contracted and which are in red on the picture, and they will form a V, and on this V you will have a forest of trees. Okay, so I will consider mainly, but not only, but mainly two-dimensional walks with small steps. Small steps are steps which are of this form, so either the plus or minus 1, 0, or 0 plus or minus 1, or the obliques, so these are the straight steps, or the oblique steps, for which the values are plus or minus 1 of the coordinates. Okay, so these steps have been very, very much studied, in particular by Mireille in many papers, and about the enumeration, especially of such walks. So here is, for example, a typical example of an excursion with small steps in the quarter plane. So you see there are some straight steps, some oblique steps, and I enumerated them from 1 to 12. So this is a typical set of paths I want to consider. So how do you construct now a map starting from such a walk? So the general construction is the following. What you do is you draw the two Motzkin paths. So if you have this walk with small steps, if you look at the horizontal coordinate and the vertical coordinate, they form two Motzkin paths because the increments are either 0, 1, or minus 1. And so I draw the two Motzkin paths corresponding to vertical and horizontal coordinates, vertically in this case, facing each other. So the paths go from here, from bottom to top. Okay. And what do we do next? We do the mating. And the mating just consists in drawing horizontal lines between the vertices of the two paths. So what you get is this. You get a kind of, I don't know how to call it, origami, or it's a succession of quadrilaterals from the bottom to the top. Okay. In the quadrilateral, so you have several possibilities, of course 8 possibilities, because we have 8 classes of steps. So here my steps, some steps correspond to straight steps. So some of the quadrangles correspond to straight steps. They're enumerated from 1 to 10 here. And there are also 2 oblique steps, which are in green on the picture. So the difference is that the straight step have one of their sides, which is vertical, corresponding to a Motzkin. In the Motzkin spite, it corresponds to a horizontal step, and corresponds to the case where one of the coordinates of the step is 0. Okay. So now what do you do? Well, you have 2 Motzkin paths, one on the left, one on the right. I'm going to contract them. And after the construction is done, then I will also identify the upper and the lower boundaries. And what we get is a collection of triangles and quadrilaterals, which form a planar map, as below. Okay, so this is the mating of trees construction in general using these small steps. What you see is that what you have here is you have this blue Motzkin path here, which gives you a tree, which is here, and the red one gives you another tree, which is here. Okay, and now you see that you can go through the faces in this way. From 1 to 12, yes, there are 12 of them. I enumerated only the straight steps for the following reason, is that so I explain what happened in this construction first. What the quadrilaterals become is either triangles when you start from straight step, because as you may remember, a step like that, in a Motzkin's path, it corresponds to a horizontal step, and I said I wanted to crush them into points. So this gives me a triangle like that. In the end, of course, you have only triangles and quadrilaterals like that, okay? And the triangles are like this one. And the quadrilaterals, both of their sides have to be slanted, not vertical, because all the vertical sides have been crushed. Okay, so what is the main idea of this talk? Well, the main idea of this talk is to contract the quadrilaterals after this stone construction has been done. So this adds some flexibility in the construction. So how do you contract a quadrilateral? Well, what you do is you take the you identify two of the four sides 2 by 2, and there are two ways to do that in a non-crossing way. So either you can, for example, identify V with W, and then you will identify VZ with WZ. So the two here you get this interval. And then you identify UW with UV, so the two faces, the two sides of the rectangle to give you this interval. Okay, so you have contracted the quadrilaterals, and of course when you do that, you in the end you still get some kind of map. Okay, so of course the other possibility is just to identify the opposite corners, U and Z, which are here. Okay. Okay, so let us start from our map, which is above, and let us do one of the four possible constructions. And what you get is, for example, this picture here. So what I have done here is very simple. If you look at this, so the dotted line here corresponded to the boundaries, the upper and lower boundaries of the rectangle from which I started, and I identify it with the red path, the red edge here. And so this quadrangle gets contracted in this way. And in this quadrangle, what I did is I took, for example, this the side of the 4 triangle here, and I identify it with the side of the 3 triangle, which is here. And of course, I do the same for the opposite sides here. So this is one of the possible constructions. So, of course, when you do that, if you start from a walk with small steps, in the end you will get several triangulations because you have several choices that can be made. I mean, the number is of course 2 to the number of quadrilaterals or oblique steps in the walk, and of course, in general, any triangulation will be obtained in several ways. I mean, there is no reason for each triangulation to have a unique way of obtaining it. So what I will do in the sequel is to show how to restrict the class of paths and to equip the map with some other structure so that you obtain a bijection. You obtain bijection. So in this way, I will produce quite a few bijections, and some of them have been known for some time, and some of them new. And so I will show you how it works. Okay, so So before that, before I show you how it works, I mentioned that sometimes you are interested in the triangulation, sometimes you will be interested in the dual map. So in order to construct the dual map, what you do, you put vertices inside each of the triangles like that. And when you identify two points, what you do is you put, so this is one of the quadrilaterals, and I said I identified this point to this point, so what I do, I add a slanted interval here, a slanted edge. And so this means, when I do that, when I look at the dual map, the dual map, the edge which goes through this edge here will also go through this edge because they have been identified. So it will go out by in this way, and of course same above like that. Okay, so it gives you a simple way to describe the dual map directly on this picture. So sometimes it's easier to just show the dual map. Yes. Yes.
Sometimes you have four valent vertices, and sometimes you have three valent vertices.
What do you mean by four valent? This one?
In the quadrangles.
Yes.
Go to the dual, shouldn't the vertices be connected to the four sides?
No, because this is not, when I do the contraction, this is not an edge. It becomes a point. After that, I will do a contraction, so I should not consider this as an edge, but rather as a point. That's the reason. The vertical edges, they don't count. Only the one which are oblique like that. Okay. Now it's possible to make variants of these constructions. For example, you could consider different types of steps. For example, here is a 3-4 step. And then you could erase the internal edges and consider that this is a face with 9 edges. So it's also possible to construct maps with more edges than just triangles. Okay, so it's a variant. Okay, and there are many more variants that you can imagine. For example, you could use paths which do not start or end at 0. As I explained before, you can still do contractions. You can, of course, think that they are not staying in the quarter plane. And or you can also, another more tricky thing to do is to identify opposite sides of the quadrangles, and then you will get higher genus maps in this way. Okay? So I will not explore all that. I will just show you some simple examples. So let us start with the simplest one, and which has been known for quite a long time. So triangulation. So this is a triangulation of the plane, and in green I have shown you a Hamiltonian cycle going through all the faces. So when you have these cycles, it splits the plane into two connected components, and each connected component contains, well, if you erase the vertices which are crossed by the cycle, what remains are two trees, okay? Two connected components, and of course, the two connected components cannot contain a triangle because my cycle is Hamiltonian, okay? And so there remain two trees, and what the path does is essentially a depth first search of each tree, okay? It goes around each tree. And when you record that in the following way, for each tree, you have either a triangle with a red side like that, or a triangle with a blue side like that. And I remind you that the vertical sides do not count. Okay. And so this gives an excursion in the quarter plane with straight step. And essentially, this is a variant of the Millins bijection, which has been known for more than 50 years now. It's a variant. It's not exactly what is called usually Millins bijection, but it's not very different. Okay, so now another example, which are prographs, and which we will generalize to recover bijection by Kenyon, Miller, Sheffield, and Wilson. So what are prographs? They are formed with vertices of two types, very simple. Either products, where you have two inputs and one output. Okay, they are oriented from bottom to top. Or coproducts with one input and two outputs, like that. Okay. when you have these vertices, so of course each output can then be used as input in another vertex, okay? And in order to build a prograph, what you do is you stack all these vertices so that in the end you get only one input and one output, okay? And you do that in a planar way, okay? It turns out that these prographs are as counted by standard Young tableaus of regular shape, 3 times n. And they are in bijection with tandem excursions. Tandem excursions are excursions in the quarter plane with this kind of steps. And they are enumerated by these numbers because it's very actual actually, because it's a version of the ballot problem with 3 candidates. And given the political situation of France, it should be relevant in the next weekends. Okay, so how do you do the construction? Well, you will have 3 types of cells corresponding to the 3 types of steps, which we call A, vertical step, C, horizontal step, and B, a diagonal step here, oblique step. Okay, so type A, type B, and type C. And there is only one oblique step, type B. So what I have to explain is how to contract the type B step. And then it is very difficult, very simple, sorry. What you have to do is it's leaning on this side, on the right, okay, I stop with this because, okay, it's leaning on the right, and you just accompany it so that the U is matched with the Z here, okay? And this is this is the only thing you have to do. And now, take a tandem excursion, that is an excursion in the quarter plane. And what you get is, if you look at the dual of the triangulation, what you get is a prograph, okay? And of course, the A steps correspond to products. The C steps correspond to co-products. Sorry, the A steps correspond to co-products. The C step to products. And so here is an example, a simple example. And actually, it's not very difficult to check that this is a bijection. Okay. So now a generalization to maps with a bipolar orientation. So this is related to the work by Kenyon, Miller, Sheffield, and Wilson. So what we do with the previous construction, we generalize with walks, with steps. So we have this step here, 1 minus 1, this oblique step, and then we take all possible steps which are on the upper left corner, on the northwest corner. Okay, so of the form minus ij, where non-zero vectors with coordinates minus ij. Okay, so I won't go into long details, but just to say how do you do? Well, you will have faces which look like that. They will have a minus I and a j coordinate. And so as I said, when you have such a step, you can consider it as a big face. And you orient the faces from west to east. And for the quadrilaterals, these are the only ones that you are going to contract. You orient them again from west to east. And then you see that the orientation is compatible with the identification that you are going to make. So here is an example, which is the one that is in the paper by these authors here. And you see what you do is you just construct this thing here, and what you get is a map with a source which is here and a sink which is here. Okay, and all the edges should be oriented from the source towards the sink. Okay, so I will not describe anything more, but because essentially I've described everything here. You know how to do the construction. It's very simple. All you have to do is to contract these quadrilaterals. Okay. Another example, which I've never seen in the literature, although it's very simple and natural, which I call reversed Y walks. So these are walks with this kind of, oops. What happened? Okay. No problem. So these are walks with 3 kinds of steps. One vertical step, which is a straight step, and 2 oblique steps, which go down. Okay. So when you have such a walk, and for example, if you look at an excursion with such steps, so the vertical coordinate will perform a dig path because it has only plus or minus 1 increments, and the horizontal will make a Motzkin path. But the horizontal steps will move only when the vertical. There will be horizontal steps when the vertical coordinate moves up. Okay, and of course, that you can see from the picture. Okay, so what does this model correspond to? Well, it corresponds to maps, what I call maps with a complete spanning tree. So we start with a trivalent map, like that, on the left, A. And what we do is we cut edges until we get a tree, okay? And we keep half edges, which are called buds, or maybe you could call this also a blossoming tree. And we choose a root somewhere. Here I choose a blue root. So when you put this like that, so you get a tree, a binary tree in this case. And if you want to recover the original map, what you have to do is to match the half edges here, which are the leaves of the binary tree. Okay, so how do you encode that with reverse wide walks? Well, it's very easy. What you do is you have 2 types of oblique steps. What you have to do is give the rules for constructing the steps. So this is very simple. What you do is always the same thing. You identify the northwest and southeast corner, like that. U with Z in both cases. Okay. So this is just the only rule that you need. And so how does it work? Well, what you do is first I first look at what happened on the right, which corresponds to the vertical coordinate. What I construct when I start constructing the dual map is I am constructing a binary tree which corresponds to the Motzkin path on the right. This is a standard bijection between binary trees and Motzkin paths. Okay, and what do I do when I look at the left? Well, I have a binary tree, and so I have yes. Yes. Sorry. Yes, I mixed up. Yes, all these are dig paths on the right. On the right is a dig path, and on the left, what I have is a family of buds or leaves of the binary tree, and I need to pair them in a non-crossing way. And this is just done by a usual bijection between dig paths and non-crossing partitions, non-crossing pair partitions. Okay, which is an obvious bijection that everybody knows. So it's a very simple model and very natural bijection. Apparently, I have never seen it in the nature. Yeah. Oh yes, but they are given. No, there is only one way, which is dictated by the work on the left. Here I have only used the work on the right, the vertical coordinate. Then now I use the horizontal coordinate to do the pairing. Of course, if I change the horizontal coordinate, I will have another pairing. But it will be always a non-crossing pairing because by construction, the dig path will give me a non-crossing pairing. Okay, so that's step B. Okay, of course, instead of using step 0.1, you could use instead step 0.2. And as I said before, you can extend the thing and get a quartic map. And then on the right, you have a bijection between some generalized dig paths and these are ternary trees, and on the left you do the same. And actually you can even generalize further and take steps like this, okay? And what you get is a bijection between rooted maps with complete spanning trees and generalized random reversed Y walk. Okay, so this is fairly simple. How much time do I have?
1 minute.
1 minute. Okay, so that's perfect. So I will go very briefly. So there is also it's also possible to recover a bijection by Bernardi with Creveras works with the same construction exactly. Okay, so I skip the details. And finally, another bijection between Works and Schneider Woods, which originate from the work of Bernardi and Bodichon, and which has been revamped by Leeson and Watson recently. So again, I don't go into the details because it's. But again, with a very simple rule, you just recover the bijection with almost no effort. So here's the final picture. So. Conclusion, so what I have shown is how to produce triangulations, more general maps, from works in the plane. So this construction has a very, very simple principle, as you have seen, and we recover several non-bijections which have been obtained. Usually they have been described in a recursive way, so here we don't do it recursively, we just do it globally. And of course, as I said, many variants are possible, and hopefully you can use them to produce more bijections. And I think it's time to say happy birthday, Philippe.
Questions to Philippe?
Ready?
How do these bijections help the enumeration?
Okay, so I said no formulas, so I said no enumeration. Some of these have some enumeration, some of these don't have nice enumerations, but well, if you know how to enumerate works in the quarter plane, which is one of the favorite activities of Mireille, then of course you can use this kind of construction to enumerate maps if you are able to make the translation between bijection between the two. In all the cases I think in most of the cases I have shown there is some enumeration, but not enough, but in most of them.
But the weight of one configuration or one triangulation will not be 1, I guess.
What?
I mean, the weight, the statistical weight, if you enumerate the triangulations,
Yes?
then you can, you have this, the entropy.
Oh, no. The triangulation comes with some additional structure, or the map comes, for example, we have seen a map with a spanning tree or thing like that, or
Yes,
a map with an orientation.
So you have the entropy of the
No,
spanning tree.
you when you enumerate, you enumerate, if you enumerate, the paths are easier to enumerate, but when you enumerate the paths, what you get is an enumeration of the map with some weight, of course. It's not a direct enumeration of maps, it's an enumeration of weighted maps, which may correspond to some statistical model. Yes. Yes?
In the work of Sheffield, there is another construction which he calls hamburger cheeseburger or
Yes.
quantum inventor. So
Yes, no,
I was wondering if there is a connection.
I have not looked at that carefully, so I cannot comment on that.
It's a reformulation of a POTS model in some sense on maps. So
Perhaps,
I'm
no,
wondering
but
don't
yes, I should look at that surely, but I have not looked at this construction.
Like cheeseburger.
No more questions? Okay, so we have to head to the restaurant.
Thank you.